Hey, welcome Advanced Geometry students. Today we're going to talk about law of sines. So far we've been discussing using trigonometry, SOHCAHTOA, with finding different side lengths or angle measures in a right triangle. But you can also use trigonometry to find missing angles or side lengths in non-right triangles or oblique triangles. All right, so that's today's focus. And then there's also law of cosines, which we'll do on Wednesday. Gives you another relationship that you can use for oblique triangles as well. So the first thing we're going to do is we're going to derive the law of sines. So before that, whenever we're dealing with trigonometry, study of triangles, typically triangles are labeled in such a way that lowercase a, this little variable for an unknown side length, is across or opposite the triangle from angle A. And lowercase b, that little unknown side length, is across from capital B or angle B, and so forth and so on. So whenever you're reading a problem and it refers to a side length of C, you can assume that it is opposite angle C, and side length of A is opposite angle A, and so forth and so on. All right, so here we go. First step to deriving this is to turn it into right triangles. So I'm going to start by drawing an altitude, and I'm going to set up two right triangles, and I'm going to call this unknown side length here H. Alright, so I've got two right triangles here. Let's fill these in so we can focus on them a little bit. So I have the gray triangle and I have the yellow triangle here. So let's do the gray triangle first. Alright, in the gray triangle, I know that the sine of angle A, sine is opposite over hypotenuse. In a right triangle using SOHCAHTOA, sine is opposite over hypotenuse. So the sine of A is equal to H over C. All right, now for the yellow triangle. In the yellow triangle, I know that the sine of C is equal to opposite, which is H, over hypotenuse, which is A. So the sine of C is equal to H over A. All right, now, if I multiply both sides of this equation by C, I get that C times the sine of A is equal to H. And if I multiply both sides of this equation by A, I get A times the sine of C is equal to H. And the reason I wanted to do that is because in the original triangle, H didn't exist. So my goal is to get rid of H, and I'm going to do that by substituting. So in this first equation, instead of H, I'm going to substitute in its place A times the sine of C. So I have C times the sine of A is equal to, and instead of H, I substitute what was equal to H, A times the sine of C. And then finally, to derive my formula, I'm going to divide both sides by CA. So the C's will cancel here, and the A's will cancel here, and I end up with that the sine of angle A divided by side length A is equal to the sine of angle C divided by the side length of C. And this is the law of sines. So to write it down in our note sheet, the law of sines says, go back and take a look, that you have the sine of the angle divided by the side length opposite it equals the sine of another angle divided by the side length opposite it. So I'm going to say that the sine of A over A would have to equal the sine of B over side length B, which would have to equal the sine of C over side length C. It's actually pretty easy. All right, so let's apply it now. All right, so the first way we'll use this is we'll use it to find a missing side length. Now to do that, what's really important to use the law of sines is to make sure you have the established relationship necessary. So what I mean by that is I know this angle and I know the side length opposite it. I know this angle and I want to find the side length opposite it. So I can apply my law of sines to do that. So I would say the sine of 70 divided by 22 has to equal the sine of 42 divided by x. And now I can just solve for x by using cross multiplication. When I cross multiply, I get x times the sine of 70 is equal to 22 times the sine of 42 degrees. And then finally, I'm just going to divide both sides by the sine of 70. So x will equal, let me pull out my calculator here and punch this in. I need to make sure I'm in the correct mode. Alright, so remember you have to be in degree mode. My calculator, every time I restart it, defaults to radians. And remember, the thing you could always do in your calculator is do sine of 30, and it should equal 0.5 if it's in the correct mode, which mine is. So x is equal to 22 times the sine of 42. Be very careful you close this parenthesis before you divide by the sine of 70. So x was equal to this 22 times the sine of 42 divided by the sine of 70. X is around 15.6, 15.7, I guess, centimeters. So we'll say about 15.7. And then just make sure your answer makes sense, right? Remember, in a triangle, the biggest sides across from the biggest angle. So if this is a 70-degree angle, 22, it needs to be bigger than the side across from the 42-degree angle. So 15.7 makes sense. All right. So we're going to do the exact same thing, but there's one little thing I've changed here, and I want you to notice is, remember, in order to do this, the relationship you need is you got to have an angle and the side across from it, and then you got to have an angle to find the side across from it. So what's happening here is that I do not know this angle, but in the triangle sum theorem, all the angles in a triangle add to 180 degrees. So if I subtract 60 and 58, I get that this is a 62-degree angle. So just be very careful that you're making sure to use an angle and the side across from it, angle, side across from it, to use law of sines. So I've got that the sine of 62 degrees over x is equal to the sine of 60 degrees over 6.5. Then I'll cross multiply, and I'll get that x times the sine of 60 is equal to 6.5 times the sine of 62. Then I'll divide both sides by the sine of 60, and I'll get x. And let me just get my calculator out, punch that in. So I've got 6.5 times the sine of 62, closing my parenthesis, being very careful, divided by the sine of 60. And I get about 6.6. If this is 6.5 and it's across from the 60-degree angle, then the one across from the 62-degree angle should be slightly bigger, and it is, so this answer makes sense. There we go. All right, and then the last thing we can do with the law of sines is we can use it to solve for missing angle measures. All right, and remember, when we're solving for missing angle measures, that's when we use the inverse sine option in our calculator. And I'll show you when we do the examples. So again, establishing the relationship. I got angle, side across from it. I want to find this angle, and I have the side across from it. So I know that the sine of 42 degrees divided by 15 is equal to the sine of theta divided by 13. Now my objective here is to get this by itself. So I will cross multiply, all right, and I will get 13 times the sine. Actually, instead of cross multiplying, let's make this a little easier. I'm just going to multiply both sides by 13. So I would get that the sine of theta is equal to 13 times the sine of 42 degrees divided by 15. And so now all I'm going to do in my calculator is I'm going to inverse sine both sides. All right, because inverse sine of sine just gives me theta. And then I'll inverse sine all of this as well. And I'm just going to do that in my calculator. And I'll show you exactly what I punch in here. So I got inverse sine, so second sine, 13 times the sine of 42 degrees, being sure to close my parenthesis, and then dividing by 15. Then I close the entire parenthesis, and theta is around 35.4 degrees. And I didn't really say how to round it, I don't think. So we'll just say, for the sake of this problem, around 35.4 degrees. Just pay attention to what it asks you to do. All right, and the next example, okay, similar thing. We'll work this out. Then I'll point something out to you. So first thing, relationships. Angle, side across, boom. Solving for angle, I know the side across, boom. So I got that the sine of 72 degrees divided by 15 is equal to the sine of theta divided by 15. I'll multiply both sides by 15, just like I did in the previous problem, and I get that the sine of theta is equal to 15 times the sine of 72 degrees divided by 15. Then I will inverse sine the entire equation, so both sides. Inverse sine and sine cancel, giving me theta. And then when I inverse sine this stuff on the right, I'll punch it in my calculator. Oops, forgot my sine, sorry. 15 times the sine of 72 divided by 15. And let's just punch that in and see what we get. So I got second sine 15 times the sine of 72, closing that parenthesis, divided by 15, and I get 72 degrees. Now, if you were paying attention in the beginning of this problem and you're thinking critically, you guys should have known without having to do any work that theta was 72 degrees. Because if these sides of the triangle are congruent, they're both 15, then the base angles are congruent, which makes theta 72 degrees. And I did this intentionally because I want to point out to you is don't overcomplicate things. Think critically about the problem you're being asked to solve, and it could save you some work down the line. All right, so you just have 5 problems in your daily assessment where you practice this concept. And as always, just reach out if you need any help or anything, all right?